Hello everyone, welcome to my channel. And last time I built a circuit, and this is the circuit I built. This is a pulsating LED project. The purpose of this module is just to show the pulsating LED when you connect an LED directly to the secondary of the transformer. We can see that in the dark. Kill the light. That is the pulsating LED. When you connect an LED directly to the secondary windings of a 12 volts transformer, and that 12 volts is a voltage BRMS, and we proved that in our previous video. So now, what is the drawback or the disadvantage of this circuit? It seems that it's very bulky, very big, and I'm using a lot of PCB, very heavy, lots of headers, output header, input header to the transformer, and we are trying to build now a power supply that has a good efficiency. So instead of building modify this type of LED circuit, pulsating LED, I now design a half wave rectifier using this module. You see the transformer is inserted inside, unlike the previous one, and also the PCB is almost or I cut the PCB, small portion of PCB I used, and instead of this, as you have seen here, let us take out the output LED. This PCB is very big compared to our new design, and this is a transformer module. Now this is our new transformer module with less PCB I used and less header, just an output header, 3 pin. Unlike here, I'm using too many headers. And you can patch the output of the transformer, secondary output, through the header, 3 pin, only just a 3 pin header. Here, 2 header. So I reduced the cost of building a transformer base module. You can see here, when I connect the LED, we get the output. In here, we can also connect here this LED with our new design transformer module by patching it. Since I don't have the female, we can go like this. Okay, this is the output. I don't have the female, so I'm going to so hard. We can, oh, so hard to patch because it has no output design for external output. So now that is again the problem. I don't have an external output for this module. Aside from I'm using a lot of PCB and the header, so I decided to redesign the module using this rectifier module. Big capacitor here. We have the input header, the output. This is the new feature jumper for onboard LED and for the output, external output. If you're going to slide this jumper, you can connect now your external output. This is a half wave rectifier module. So we can now see how to use this module. Unlike the other one, it has no external output provision. I have this one. This one is just an additional output for additional output. But here I can use an onboard output or external output. That is the new features. Aside from this is detachable. You can just insert it to the transformer base module. And we have now this, the transformer half wave rectifier, detachable, and it fits to the case, unlike my previous design, this one and also this one. This is center top, and this is half wave without half wave rectifier, without capacitor. This time we have the capacitor, and we have this half wave rectifier. So from this very big bulky design, we got now this slim type and detachable with external output header. Aside from detachable design, you can detach it and use the transformer inside. Okay, and let us now see the diagram of the half wave rectifier, how to design this rectifier. We have the circuit, 220 volts, 220 volts to 0 volts, primary winding, secondary. I'm using multiple output transformer, 12 volts. We have different voltage values here, but I'm using 12 volts output. We have this diode 1N4007, our rectifier, filter capacitor, 3300 microfarad, 25 volts. This is 25 volts. And we have the load resistor and the LED. This is 25 volts. So what is the operation of this half wave rectifier? It goes like this. In the primary windings of the transformer, we have this AC sine wave, the direction, a very big sine wave into the primary windings. Because this is a step down transformer, it converts the 220 volts to 12 volts. Current flows into the coil, inducing a voltage, producing a current to the secondary windings, and then we have these 12 volts. These two has a ratio, depends on the number of turns of the coil. windings of the transformer. So it means we have these 12 volts. I'm using 12 volts. And the 0 volts, the two terminal. So from here, the sine wave, very big sine wave, then it goes to the secondary windings, it becomes a small sine wave. And then the waveform, always others don't forget to tell you what is the design or what is the behavior of the waveform, sine wave. It's so hard to imagine what this sine wave really is. Actually, this AC sine wave or this alternating current sine wave reverses direction like this. When this is positive, this is negative. Negative, it's positive. Happening at the same time. They is instantaneous. Just like a seesaw. If you know the seesaw, when the other end is up, the other one is down. When the other one is down, the other one is up. That is the seesaw effect of the alternating current. Just like this one. A small sine wave produced by the secondary windings of the transformer. What happened to the positive half cycle of the secondary windings is it passes to the diode, making it a forward bias, the positive half cycle, and then goes into the capacitor, charging the capacitor, and then flows back into the ground. And then how about the reverse voltage? This is what happened. This is the direction. It indicates the direction. Since we know that this is like a seesaw, it happens at the same time. There is a positive voltage also, but in different direction. What happened is this during the reverse. They said that in the reverse direction, this one, there is also a positive voltage. When this is positive, this one is negative. This is negative, this is positive. So the positive half goes into the capacitor and then flows into the capacitor and making this LED, or I mean this diode, in reverse bias. So what happened is there's no output. Once the positive half cycle passes through the rectifier or our diode, I'm using 1N4007, this is the output waveform, the half during the positive half cycle. How about during the reverse direction? This is the reverse direction. See? It did not pass to the rectifier. That's why there is no output. The same line, orange. And the sum of the two output happening at the same time is this. So others explain this in shortcut, but this is actually the actual waveform reversing its direction. See the other positive half cycle into the right side. There's no output. So when it passes to the capacitor, this other positive half cycle in reverse direction, it just make this capacitor helps to discharge the stored voltage charge, and at the same time it flows into the load. What do you think? Which one is supplying the current to the load? Is it the current that flows into the diode or the capacitor? It is the capacitor that supplies current to the load. So during the positive cycle, it charges the capacitor, and during the reversal of the wave, still there is positive on the other end. It helps to push to discharge the capacitor. So it's happening at the same time. Charging, positive cycle, still there's a positive cycle, reversing direction. Equals to this node, it will help discharging the capacitor to the load. So this is now the output. The output of the half wave is this, pulsating. With the use of capacitor, it helps to delay smoothing out the flat side of the output. Just like this one. Patching during the zero value, that's the time the capacitor is discharging. So this is equivalent to 1 cycle. This very big discharging effect of the capacitor, very big waveform. And if we have 3 cycles, this is 1 cycle, we have 3 cycles, we have this pulsating direct current with a smoothing effect of the filter capacitor. What is the value of the capacitor I use? 33,000 microfarad. Why did I use 33,000 microfarad? 25 volts. The bigger the capacitor, the smoother the waveform. If you have 4,700 microfarad, you can use that to make a smooth waveform. So this is now what happened to the reversal, the direction. Reversal direction of the AC waveform. That is the behavior of the AC waveform. I'm using 1N4007 and 3,300 microfarad, 25 volts, that's not 16. So in here, can we compute for the value of the resistor in series with the LED? And what is the voltage output? That is the question. And that's we're going to find out how to compute for the values of RL and the voltage output of the load. And also, this is a power supply. We're going to compute for the efficiency of the circuit or the power supply. Let us do that. Okay, let's analyze it again. We have now the 220 volts BRMS. This is in BRMS. What I mean by BRMS is located at this sine wave form. Sine wave. BRMS is located somewhere here. Voltage peak is located at the peak. BRMS located around almost near to the voltage peak. So okay, and now we are now going to compute for the B voltage peak. Why we are going to compute for the voltage peak? Because that is always used in the computation, not the BRMS. That is voltage peak to peak of a sine wave. So in 12 volts secondary windings, this is 12 volts BRMS, and we know that using our project in our last video, that it creates a pulsating LED lights. So in here we have 12 volts BRMS. We're going to compute for the voltage peak by using this formula. Also, I used this in the last project. So using 12 volts, I'm using 12 volts. We got BRMS equals 0.707 times BP. BP now is, since I know BRMS, it's the 12 volts. That is the voltage rating of the transformer you buy in the market. We got 16.973 volts. And since after passing the voltage BRMS to the diode, we got a new BRMS value. This is a BRMS computed for half wave rectifier. BRMS now is voltage peak over 2. We computed that voltage peak of the transformer secondary windings. Transformer secondary windings. The BRMS here. Voltage peak divided by 2. We have now a new value of BRMS, 8.4865 volts. That is the BRMS now after the signal or the current flows into the diode. We get a new BRMS value, 8.4865, by using this formula. BRMS equals to BP divided by 2 for the sine wave. And now, here is the voltage average. Also equal to voltage DC, also equal to voltage output. That is what we're going to solve, voltage output. So since they are all equal, voltage DC, average, and voltage output, we have a new formula. Voltage average, 0.318 times voltage peak. As I've said, we are always using voltage peak in the calculation because that is the sine wave we're going to use. 0.318 times 16.973 volts voltage peak. We got now a voltage average or voltage DC, that is the direct current voltage, 5.397. So in this waveform, we got an AC voltage and DC voltage. We got here 8.4865 AC voltage and 5.397 DC voltage in this pulsating direct current. So you have seen here, the purpose of the rectifier is to convert AC to DC. Since during the rectification, now the current flows in one direction because of this rectifier. We're going to solve now for RL using KBL. So we need a voltage source. What do you think is the voltage source to be used? Is it the 12 volts BRMS or the voltage peak? Always, as I've said, we are now going to use the voltage peak. Always use voltage peak in the calculation. That is the input voltage. Voltage peak. Voltage supply minus voltage RL, voltage D2 is equal to 0. Now we got this voltage peak 16.97 minus 2 volts. Voltage drop across LED to turn on. We got 14.973 volts across the load. Ohm's law, substitution, current rating of the LED to turn on, 0.02. We got 748.65 ohms. I use 1 kilo ohms available. Then we know the value of RL, the voltage output, which is also equal to voltage average or voltage DC. We're now going to compute for the efficiency of our power supply, which is equal to power of the output, power input times 100%. We're using this eta symbol, a Greek symbol, which is equal to power of the load, power consumed, or power output divided by the power input times 100%. Since P is equal to BI and I is equal to B over R, substituting B over R to I becomes B squared over R. So B squared over R, B squared over R, voltage of the load squared over R of the load, BIN squared over R of the load times 100. Since we know What is the voltage of the load? That is BO, BDC 5.397. This is the voltage consumed, or I mean the voltage of the load, squared over R from this formula, R 1000, the resistance of the load, over the, now we're going to use this BRMS. That is the input voltage, 8.4865 squared over 1000 times 100. We got now 40.1%. That is the efficiency of this half wave rectifier. And it is seldom used today because it's inefficient. It has only an efficiency of 40.1%. You can use this for a charger. Battery charging, you can still use this for battery charging application using this circuit. So in here, we are almost finished. We got this new module, a detachable design with the external output capabilities by sliding the header. I have this, my schematic diagram. I have the transformer output, and then goes the return. Output of the transformer is going to the rectifier input. Now we have the rectifier output. It depends on the settings of the jumper. If you're going to use the onboard LED or the external output, just slide the jumper settings, change the settings. I had this transformer module. We saw that in our demo. And then we have this rectifier module. We have the input and the output. And we're going to check if the external output of this rectifier is working by patching this. Let us use this. Okay, we can now use this. Okay, we have the positive, negative, then we're going to patch the output to test the output, and then change the jumper settings. Now we have this, the output of the module. We're going to connect this in here to our LED. Positive to positive, negative to negative. Positive. Okay. And now we're going to see how many LEDs, external LEDs, is going to work. Seems nothing. Let us see this. Okay, positive, positive, negative, negative. Positive. Not working. Why is it not working? This one is, oh, negative. Should be negative. Okay, negative, positive. Let us now check. Nothing. Why is it not working? This is now going to be the positive. Oh, something wrong with the switch. Let's now slide this. What's wrong with the jumper? Okay. Still no, we're getting no output here, but anyways, I test this in the past. Let's now check again, one by one. Then the negative, still not working. Okay. What's wrong with the circuit? Should be negative. So, thank you for watching the video. It seems the external output is not working. And we're losing time testing this. Because wrong polarity. Yeah, that one. We have now this. After a very long time, we get the output. 1, 2, 3, 4, 5, 6, 7, 8, 9. It can light up to 9 LED in series. Since it works on voltage peak 16 volts, it can light 9 LED. We're having this external output. Okay, thank you for watching the video. Bye.